the cloud. Okay, so Top Hat, I'll post the code later today, so you'll have access to those. Those questions are intended to be easy. These questions are intended to be just like as basic as they get. I was talking with some of your classmates before class about exams and preparation for the exams. I do have old exams and I'll share those with y'all. Though I do want to say that I always do that with a little bit of reluctance because sometimes I do class, or I do a class where it's multiple choice exclusively, and then where it's multiple choice and short answer. But I'll give you some of the questions so you can kind of see the style that I'm going for. But I do want to caution you, anytime that you look at an exam, think about, okay, what did we cover in my class and what's covered on this exam? If there's something on that exam that, or that, yeah, that copy of that exam, and you say, oh, well, I don't remember ever talking about that. You're not wrong. It's not a misconception or you missed something. Probably just didn't talk about that. In addition to that, the way that I write exam questions, or the way that I kind of break down my exams is I treat them in different fractions. So I look at basically a third of the questions are going to be kind of the easy questions that I expect everyone's going to get. And that's not a hard and fast, like, oh, like the exam was 30 questions, so there will be exactly 10 that are this form. Instead, it's just my rough idea of, oh, this is where it is. And I would be comfortable saying that, you know, that's plus or minus 4% or something. So there's going to be a fraction of them that everyone should get. That's my expectation. Then there's a middle portion that's about half of the exam that are a little bit, or they are more challenging than that. Not everyone is going to get those. And then there is a last fraction, approximately 1/6 of the exam is going to be challenging questions. And the way that I always kind of think about it is your easiest questions are going to be kind of just the definition, almost like, what is a diastereomer? And then the next level question would be, well, what is a diastereomer? You'd have to recall that information and apply it. Here's 2 images or 2 sugars. Are these diastereomers? So you're having to recall what a diastereomer is and does it apply in the circumstance of these 2 sugars or these 2 molecules. And then the way that I can make that even more challenging is by saying, all right, well, to answer this question correctly, you have to have the understanding of what a diastereomer is, apply it to these 2 molecules, and then bring in another definition to say why these are not diastereomers, just that as an example. So you're kind of recalling 2 unique places where you're getting information from, and then you're applying it to one kind of model. So that's kind of my hardest chunk of the questions. So at any rate, I think that I'll be able to elaborate on some of those as we get into some more of our content here. But in the meantime, we're going to go on to free energy. We're going to touch on glycolysis. And then today, what we're going to dig into quite a bit is we're going to dig into polysaccharides, monosaccharides, disaccharides. We're going to be talking about sugars and structures of sugars. So free energy, or the free energy change, delta G, of any reaction is related to the ratio of equilibrium and non-equilibrium, also known as your initial concentration of your products and your reactants. We looked at this just the other day, or just yesterday, and we can kind of combine that to give us this overall equation. Now, free energy change is a measure of how far a reaction is from equilibrium. Now, standard free energy change, well, under standard conditions, the initial concentrations are 1. So that would mean the natural log of 1 over 1. Delta G is now called delta G naught, which is your standard free energy change because our initial conditions are defined standard conditions. Now, this is different from a biochemist standard state where a biochemist standard state, we're not going to use 1 molar of a particular solution just because when you're dealing with 1 molar of a hydrogen ion, that would give you a pH of effectively 0. Now, this equation right here is going to be valuable for you to recall. Delta G naught is equal to RT. R and T I would provide you with. But your R is a constant in your T, considering that you're doing this at standard conditions, you're going to have a standard temperature of 298 Kelvin. And that just leaves you with the natural log of KEQ. And that's that ratio. That's not made good. Standard free energy, we have basically a relationship here between our standard free energy change, our delta G naught prime on our y-axis, and our equilibrium constant, KEQ prime on our x-axis. Since KEQ is a constant specific for each reaction, then delta G naught, or delta G naught is also constant specific for each reaction. Because KEQ can be measured experimentally, we have a way to determine our delta G naught. So we can look at, under certain conditions or under equilibrium conditions, what is our ratio? And then we can calculate the free energy change for a reaction. If KEQ is less than 1, we should expect delta G naught to be greater than 0. Reactants predominate over our products. The reaction proceeds to the left as it approaches equilibrium. So it proceeds to the left, thinking about on the left-hand side, you have your reactants, on the right-hand side, you have your products. So if KEQ is less than 1, we're going back towards our reactants, as opposed to going towards our products. Now, if KEQ is greater than 1, delta G naught is going to be less than 0, in which case our products are going to predominate over our reactants. The reaction proceeds to the right as it approaches equilibrium. So the values that I will provide you with through this sort of calculation, well, I'll give you the 0.008315 kilojoules per mole Kelvin. Temperature is 298 Kelvin. Effectively, you can take that RT to be 2.48 kilojoules per mole. So that kind of saves you a little bit of a step and saves you the stress of doing that. Just remember, this times 298 is 2.48. And when you're dealing with reaction under standard conditions, that 2.48 is what we're going to be looking for. And what this also gives us is our extreme ends of this graph right here. When our KEQ is equal to 0.001, then we have a delta G naught of 17 kilojoules per mole. When KEQ is 1,000, then our delta G naught is negative 17 kilojoules per mole. So this is just showing the extreme ends of, well, where is our KEQ? Is our KEQ 1,000, where it strongly favors our products? Or is it considerably less than 1, where it's strongly favoring our reactants? If our reaction strongly favors our products, would you expect that reaction to proceed spontaneously? If it favors the products, absolutely. Do we see that represented with our free energy change? We do. We see a negative free energy change. So that's a favorable spontaneous reaction. On the opposite end of the spectrum, KEQ of 0.001. It's a low KEQ. So when you think about the relationship of products over reactants, well, that would mean we have a very small amount of products per reactant, or compared to our reactants. So that means that our reaction is very unfavorable, going in the direction from left to right. Does everyone follow that? Okay, great.
Wait, you said our reactant is unfavorable?
So this right here on the left-hand side, where you have a KEQ of 0.001, if you think about, if you were to write 0.001, okay, what ratio of products to reactants would give us a value of 0.001? Well, let's say that we had 1, and I always like to think about an individual product. Well, how many reactants would we need to get a ratio of 0.001? Would we need 1 reactant? No. 10 reactants? No. 100 reactants? No. How about 1,000 reactants? 1 divided by 1,000, would that get us 0.001? I believe it would. So, sorry, there's a chat. Yes, yes. I apologize for anyone adding to the chat. I'm not exactly the fastest with responding to that. But yeah, so effectively what this means is if you were to put these reactants in a container together, and let's say hypothetically, you have reactants A and B, or just let's make it simple. Let's say reactant A converts to product B. If you had 1,000 copies of that reactant, and you had a KEQ of 0.001. From that 1,000, only one product would basically spontaneously be produced. Everything else would be like, well, I'm good. I'm staying as a reactant because we've reached this ratio. If you flip that and you say you have 1,000 copies, let's say now go over here. We have a KEQ of 1,000. That's effectively the same as 1,000. Doesn't really get any better whenever I try to write over where I've not written very well. 1,000 over 1. So let's imagine that you had reactant A in a container, in a beaker, and you said, all right, what's going to happen? That reactant is going to convert to the product. And progressively, as we proceed through where each reactant is converted to a product, those product concentration is going to go up, the reactant concentration is going to go down, and ultimately what's going to end up happening is we're going to get about 1,000 of those products in one of those reactants, and then it's just going to stop and so say we're good here. And so that will proceed swimmingly, that will proceed spontaneously and without the addition of any outside force or energy. Does that make sense? So, you know, I taught Gen Chem 2 this past semester, and it had been a handful of years since I taught it, and it had been even longer since I took it. And my walk away, or I talked to, I don't know if anyone had Dr. Patterson, Dr. MJ Patterson, but I talked to her at the end of the semester, and I was like, you know, it's been a minute or two since I took Gen Chem 2. And I remember really struggling through that class because I was like, this is nothing like Gen Chem 1. I feel like I was sold a bill of goods whenever someone's like, yeah, sign up for the second one. It's kind of like you watch Star Wars: A New Hope, and then you're like, all right, cool, I want to see the sequel. And then somebody's like, how about Deep Blue Sea starring LL Cool J from 2001? And then you say, none of the characters are really the same. There's struggle, but now there's a shark attacking people. But I summed up Gen Chem 2, and I felt like I summed up Gen Chem 2 with, I feel like the last half of that class is just ratios. Do you understand, bless you, do you understand what a ratio is? And that's a big part of this class because we talk about pHs and pKa's and what is the ratio of this form of a molecule to this form of a molecule under these particular conditions. Okay, so we'll proceed from there. Okay, so free energy change, delta G of any reaction is related to the ratio of equilibrium and non-equilibrium concentration of the products and reactants. Now, when we talk about reactions taking place, this is kind of what we left off with yesterday with coupling of reactions and combining of reactions. So two of the reactions in the metabolic pathway for glycolysis are as follows. Fructose 6-phosphate plus ATP yields fructose 1,6-bisphosphate plus ADP and a single protein. With a delta G naught of negative 14.2 kilojoules per mole. Favorable reaction? Yes. Okay. Now, this is our pathway for glycolysis. What we talked about yesterday was we talked about that right there. What we're jumping into right now is this going to this. So fructose 6-phosphate, this is fructose 6-phosphate. It's phosphorylated on carbon number 6. It is a 5-membered ring. It is a sugar. It gets phosphorylated by transferring a phosphate group onto carbon number 1 right here. that gives us fructose 1,6-bisphosphate. Okay, so we've added another phosphate group. That's a favorable reaction. So if we look at this right here, this fructose 1,6-bisphosphate molecule, we've got a phosphate group on carbon 6, phosphate group on carbon number 1. Then we've got this ring, and we've got a total of 1, 2, I'll start with 1, 2, 3, 4, 5, 6 carbons. Okay, now the next step in glycolysis is to take that 6 carbon molecule, this doubly phosphorylated 6 carbon molecule, and basically chop it in two. And by chopping it in two, with the help of an enzyme known as aldolase, this is going to catalyze what's known as an aldol cleavage reaction. This is going to split our 6 carbon molecule into 2 molecules. How many carbons do you think each of those 2 carbons are? Or each of those, how many carbons do you think each of those molecules are? 3. You're absolutely right. We're going to take that 6 carbon molecule, split it into 2 3 carbon molecules. Those 3 carbon molecules are glyceraldehyde 3-phosphate on the left here, and then dihydroxyacetone phosphate on the right. We're going to revisit these in just a moment, but we're taking that, we're splitting it in 2. Now, if we can go back for a second, we're going to look at the energetics of it. This phosphorylation of fructose to get us fructose 1,6-bisphosphate, favorable. Fructose 1,6-bisphosphate being split into dihydroxyacetone phosphate and glyceraldehyde 3-phosphate, unfavorable. Now these two combined, still fairly unfavorable. But think about this pathway as a whole. We have all of these different reactions. Reaction number 1, the phosphorylation of glucose. That was a favorable reaction. Then we're going to isomerize that molecule. And so these metabolic pathways essentially are going to function by saying, all right, well, if we can get this really large domino to tip over, then that's actually going to cause these other smaller and sometimes maybe larger dominoes to tip over, because what we want to do is combine the energy harnessed from one reaction to help drive other reactions along the way. Does that make sense? Okay, great. Now, the overall reaction for these two, and this is one of the things that we did yesterday that you can continue to do. Take multiple reactions and combine them together. Now, we did that with the hydrolysis of ATP and the phosphorylation of glucose. We combined that and we saw a favorable reaction. Here we've got phosphorylation of a fructose and then cleavage of a fructose, and we can cook up this overall reaction. Do you think that there is an overall reaction for glycolysis that you can kind of look at? Absolutely. You're gonna have ATP come in, and then you're gonna have other molecules along the way come out, everything like that. So overall, these two are going to be an unfavorable reaction. Does that mean that that gums up the works of glycolysis altogether? Not necessarily. It's just something that you need to account for. Okay, well, these two reactions in a vacuum, they're going to be unfavorable together. So if you were to combine this with another reaction, then maybe you'd get something that's overall more favorable. Good? Okay. Now, so what I want you to know about glycolysis, there's a couple of things. And some of the things that I want you to know about glycolysis are kind of almost pieces of trivial information, almost the sorts of things that they'll win you beer trivia or something, or bar room trivia or something like that. For starters, your input molecule is glucose. Now, there are tons of other sugars out there. Fructose is one. Can fructose be metabolized with glycolysis as we see it right here? No. Do you think that fructose in some form or fashion, depending on the organs involved, do you think at some point it maybe feeds into this? Potentially. And do we know anything about the structure of fructose at this point in time? Not really. If anything, it might be like, oh, I could tease out some information here or here, but I don't expect you to have that background information or anything like that. So when you think about sugars like, well, other sugars, other non-glucose sugars like mannose or aldo or allose, they're going to be metabolized in different ways than glucose. These enzymes that go through this pathway are sensitive enough to say, hexokinase, for example, is going to be able to detect the difference between glucose and mannose, glucose and allose. And it's going to be able to say, well, I can metabolize, I can phosphorylate glucose, I can't phosphorylate mannose with any sort of efficiency. So what I want you to know about the glycolytic pathway or glycolysis is that you've got a pathway that's basically broken into two different parts. And these two different parts are your what's known as your investment phase, where you are investing ATP and ATP. So you have to invest 2 ATP in order for glycolysis to take place. What you will get out of glycolysis is you'll get, here's ATP and another ATP. Okay, that's great. What you will also get out of this is a molecule known as NADH. Now, I want you to know about NADH because it's kind of the quiet culprit. It's kind of the quiet, I don't know, it's the quietly very important molecule compared to ATP. ATP, okay, we get that. That's generated in the powerhouse of the cell, the mitochondria. NADH, that's, I don't know. Ooh. Well, NADH is what's known as a redox cofactor. When you think about that phrase, redox cofactor, if you break that down a little bit, well, let's just take the first phrase or the first part of it, redox. What type of reaction do you think that a redox cofactor is involved in? That's right. I've seen at least one of your classmates go like this. Oxidation reduction. You're absolutely right. Oxidation reduction reactions. Now, I say that as like, oh, this is cool. Glycolysis is cool because you're getting a bunch of ATP from it. Yay, fantastic. But this NADH right here, NADH is a molecule that's going to be fed into the mitochondria. And that NADH is going to transfer electrons. It's going to transfer electrons through this process known as oxidative phosphorylation and generate a huge amount of ATP. So when you see this pathway, I want you to think like, okay, great. Glycolysis is awesome because it can produce ATP in the absence of oxygen. Okay. But then NADH, if you are an organism that utilizes oxygen, you can take that NADH, feed it into your mitochondria with oxygen to produce a huge amount more of ATP. So if you think about an aerobic versus an anaerobic organism, an anaerobic organism or growing an organism under anaerobic conditions, oxygen limiting conditions, you're basically only going to get some of this ATP from glycolysis. Whereas under aerobic conditions, then you can use this NADH. And each one of those NADH, think about that as being equivalent to about 3 ATP. Does that make sense? Okay. Now, your chunks of the, or your portions of the glycolysis or glycolytic pathway is investment and return. The investment phase, you're putting ATP into it, and then the return phase where you're getting that ATP paid back. So you're going to basically get a total of 2 additional ATP out of glycolysis. Now, this is something that you'll dig a whole lot more into whenever you take metabolism, but I want you to understand this kind of basis and basic component of it. Okay, so now investing ATP, in addition to that, allows glucose uptake to be controlled. So glucose can either be moved in or out of the cells through transport proteins. So there are these proteins on the cell membrane that they open up and they take glucose in, and then they deposit it inside of a cell. So that means that glucose has an ability to basically move from one side of the membrane to the other side, and vice versa. However, as soon as that molecule gets phosphorylated and becomes glucose 6-phosphate, now it can't go back outside of the cell, so it locks it in there. Using ATP to irreversibly convert glucose to glucose 6-phosphate allows regulation of glucose uptake. Now, I've talked about showing some structures of sugars, but now we're going to get into kind of where sugar nomenclature and terminology comes from. There's a couple of different terms that I'll use interchangeably. Polyhydroxyl ketone, polyhydroxyl aldehyde, saccharide, monosaccharide, polysaccharide, disaccharide. All of these are terms for sugar. Some of those are redundant terms. For instance, and then last two, ketoses and aldoses. An aldose is an example of a sugar with a specific functional group. Does anyone want to guess what one of those, what functional group it has? An aldehyde. What about a ketose? Ketone, okay? Now a ketose is also known as a polyhydroxyl ketone. So if you think about a sugar that has a ketone, and then you think about that term polyhydroxyl ketone, what do you think, what's another functional group that is on that molecule that already has a ketone that we've established? Alcohol. More than one? Polyhydroxyl, yeah, multiple alcohol groups. So when you think about a sugar, think about alcohols and either a ketone or an aldehyde. Those are your signatures of a sugar. Now, saccharides, monosaccharides follow kind of a scheme like this. C to the X, H2O to the X. Glucose has a molecular formula of C6H12O6. What's the empirical formula of C6H12O6? CH2O. Remembering back from Gen Chem 1, empirical versus molecular. Empirical is lowest common denominator, and your molecular is what is actually in that molecule. Fructose, C6H12O6. Ah, crap. Glucose and fructose are the same, right? Now, what if I told you that glucose was an aldose? What do you think that fructose is? Might be a good guess that it's a ketose. Oh, but then there's galactose, C6H12O6. Ah, crap. What if I told you that galactose and glucose are both aldoses? Well, they both have that aldehyde functional group. And it's maybe been a minute since you've thought about or tried to visualize what this looks like. If we were to look at a aldose and come up with a structure that looks like this. 4, 5, 6. If we're doing an aldehyde, that means this carbon right here has to look like that. Does this carbon at the top, let's dissect this one for a minute. How many bonds does that carbon at the top have going to it? 4. Does it have a satisfied octet? It does. So it has a satisfied octet. In addition to that, is it a chiral carbon? It is not a chiral carbon. Because think about our criteria for a chiral carbon. Chiral carbon is going to have 4 different groups. This has 3 different groups. Okay, so it is not a chiral carbon. It is the source of our aldehyde. Now let's think about charges. When you see that oxygen with that double bond, and you look at this oxygen right here, is there anything, well, I can't really draw it for everyone. So there's lone pairs of electrons there, right? Do you think that when there's a concentration of 2 lone pairs of electrons, you're going to have a slightly more negative area or region than at the opposite? Yeah, so we're going to have maybe a partial negative charge there, meaning that this carbon, partial positive. Everyone follow that? Agree with that? Okay, cool. So now I'm going to draw glucose. We've got our 6 carbons. Those are all accounted for. And basically every single monosaccharide is going to follow a very similar trend. This carbon at the top, where we have our aldehyde, from your organic nomenclature and numbering scheme, what do you think that, what priority or what number would that carbon be assigned? Probably a 1. Just because, I mean, we haven't drawn anything else on there, but considering the fact that it's got a double bonded oxygen, it's probably going to be a 1. Okay, so we'll operate under the idea that that is the 1. And spoiler alert, that's the 1. So what that means is that this carbon down here, CH2OH, what's that carbon going to be? 6. It's going to be carbon number 6. Okay, now, in my opinion, and my recommendation, for this class, I'm not going to ask you to draw anything on your exams. But I think that whenever you can draw something, even if you don't have to, it might be beneficial to you whenever it comes to like recalling it and seeing it. So I always practice drawing sugars. Carbon 1, carbon 6. Carbon 6 is CH2OH. So that means we've got carbons 2 through 5. Now, specifically for glucose, we're going to have a molecule that has the following configuration. Okay, now, when you look at this molecule, we've got carbons 2 through 6. We've talked about carbon 1 quite a bit. Before we talk about any of the other carbons, have I accounted for all 6 of my carbons? Yep. Have I accounted for all 6 of my hydrogen, or all 12 of my hydrogens? All 6 of my oxygens? Yeah, I'm good. Okay, so I've drawn everything. I'm telling you that this structure right here is glucose. This is not the structure for galactose. Now, with that in mind, if that's the structure for glucose, can you see a way in which you would take this structure of glucose and manipulate it so that you could make something like galactose? And bear in mind, you don't have to be right on this. I'm not expecting you to be right on this, but how could you manipulate this molecule, any one of the carbons, any one of the positions of any of the atoms, and make it a different molecule? I saw one of your classmates do the following. You're absolutely right. Effectively, as everyone knows, this is the international sign for you move the hydroxide group from right-hand side to the left-hand side. If we took carbon number 2, for instance, and we move the hydroxide group from the right-hand side to the left-hand side, move the hydrogen to the right-hand side from that left-hand side. So essentially, we took this molecule and we redrew it as this right here. Is that still glucose? It's not glucose anymore. It is a different sugar. It's an isomer. Okay, now that's how we can look at fructose, we can look at glucose and galactose and say, okay, well, those are different from one another. Is everyone good with that? Now, before we proceed, carbons 2 through 5. Let's look at carbon number 5, for example. And let's count up the number of different groups that carbon number 5 is bound to. Carbon number 5 is bound to the hydroxide group. That's one unique group. The hydrogen, that's a second unique group. CH2 OH, that's a third unique group. And then a 1, 2, 3, 4 carbon chain. That is a fourth unique group. Is carbon number 5 a chiral carbon? Yes, it is. Same thing for 4. If you did the exact same accounting, you would see that 4 is chiral, 3 is chiral, 2 is chiral. So all of these carbons that are in the middle are chiral carbons because they're bound to 4 different unique groups. And we're going to look at that a little bit more, but there we go. Okay. So there are, these are examples of sugars that range from having 3 carbons, as we see with D-glyceraldehyde, 4 carbons, as in D-threose, 5 carbons for D-ribose, and 6 carbons for D-glucose. Triose, tetrose, pentose, hexose. If you had 7 or 8 carbons, could you still have a sugar? Could you have an octose? Absolutely. But if you think back to organic and ringed molecules, what's the size of a ring that's almost like, that's the perfect fit? 5 or 6 carbon ring, or 5-membered or a 6-membered ring are kind of your most favorable. When you get to those 3s or 4s, they're a little bit less stable. So what that means is that your 8 carbons or 8 carbon sugars are not very common. 7 carbons, you'll see a little bit of them in photosynthesis and another pathway, but overall they're not very common. So 3 through 6 carbons. If you look at carbon number, or this 3 carbon molecule, D-glyceraldehyde, you switch that hydroxide group to the other side, are you still dealing with D-glyceraldehyde? You are not. Okay, does everyone follow me there? Okay, great. Your common sugars are aldoses and ketoses. We've already looked at D-glucose as your aldose. Here we have D-fructose, where carbon number 1, 2 as our functional group of our ketone, our double bonded oxygen from that carbon right there. So that is our ketone. And that is a ketose. D-fructose and D-glucose. Your aldehyde and your ketone functional groups. Okay. Though now that I'm thinking back on it in the moment, I believe that would be carbon number 1, since that becomes your highest priority group. Can't remember my organic numbering scheme well enough to hold everyone accountable for that, because I can't hold myself accountable. Is that not correct?
Wait, so what else you should?
No, this would be a higher priority, is what I'm thinking. So that would be carbon number 1, because I just said that this would be carbon number 2, but I don't think that.
That
I
would be
think
one of
that,
the.
yeah, so then your number is 1, 2, 3, 4, 5. Okay. Well, just so everyone's on the same page, I'm not going to be asking questions that are like specific set. Because you want your highest priority to get the lowest possible numbers, so then you can change that. So anyway. Okay, so now when we look at it in aldose versus ketose, specifically when we look at glucose versus fructose, 1, 2, 3, 4 chiral carbons. D-fructose, 1, 2, 3 chiral carbons. Because this carbon right here, and this carbon right here are effectively identical because they're CH2OH. And then this carbon is your carbonyl carbon, where your ketone is. Okay. Is everyone good on recognizing the differences between these? Okay. Generally, we're going to live within the range of 3 carbons to 6 carbons. Simple sugars, here they are: ribose, glucose, fructose, galactose, mannose. These are the ones that are good to know and to be able to identify in a couple of different ways. D-ribose is an aldopentose because it has an aldehyde and it's 5 carbons. Glucose is an aldohexose. Fructose is a ketohexose. Galactose is also an aldohexose, and mannose is also an aldohexose because it's aldehyde plus it's got 6 carbons. Okay. Asymmetry, the glyceraldehydes. So here, just a moment ago, we looked at this molecule that's shown on the right. So this is D-glyceraldehyde. I said, well, if you move the hydroxide group from the right-hand side to the left-hand side, would it still be D-glyceraldehyde? And the answer is no, it would not be D-glyceraldehyde. But that's a little bit of a deceptive term because, or that's a little bit deceptive. We have to account for, this is a mouthful, our asymmetric penultimate carbon. So effectively, and there's a couple of other ways that you can designate this. In a 3-carbon molecule, you will look to carbon or a 3-carbon aldose. You'll look to carbon number 2 to designate whether you're talking about a D sugar or an L sugar. If the hydroxide group is displayed on the left-hand side, that is an L sugar. If it's displayed on the right-hand side, it's a D sugar. So whenever I said, oh, this is D-glyceraldehyde, this is not D-glyceraldehyde. Now let me rephrase that or reconsider that. The molecule that's shown here on the left-hand side, is that glyceraldehyde? Yes, it is. Is it D-glyceraldehyde? No, it's L-glyceraldehyde. So the difference between a D sugar and an L sugar is there's a couple of different ways that you can designate this. You can say either the second highest numbered carbons hydroxide group, is it on the right or the left-hand side? You could also say the highest numbered chiral carbon. Where is that hydroxide group? Is it on the right or the left-hand side? So I think that it's a little bit more helpful when we look at other sugars, like glucose and mannose and stuff like that. But one thing that's worth noting about your asymmetric or your D and L isomers of one another is that these 2 sugars are mirror images of one another. Now, when you have a molecule like this, D-glucose, okay, when you look at this structure right here, there's about 4 different questions that I can ask about this molecule that I think are worthwhile. 1, is this a hexose? Yes, it is. It has a total of 6 carbons. Is this an aldohexose? Yes, it is. It has an aldehyde and 6 carbons. Is this a D sugar? Yes, it is, because one way to consider it is my second highest numbered carbon is a hydroxide group on the right-hand side. The other way that you can phrase that is of my chiral carbons, the highest numbered chiral carbon has a hydroxide group on the right-hand side. Does everyone see the subtle differences between those? But those are interchangeable terms. Okay. Yeah, those are good ones. Okay, so when we have a molecule like this, D-glucose, we've got multiple asymmetric carbons. So multiple places where we have a hydroxide group and a hydrogen on each side, each respective side of our carbon. Here, what we see is, let's start with our molecule on the right-hand side. Let's start big picture, big umbrella. Is this a hexose? Yes, it is. And yes, I do see that L-glucose is on the bottom of the slide, but I don't care about that. Is this a hexose? Yes, it's got 6 carbons. This is an aldohexose. Yes, it is. It's got an aldose plus it's got 6 carbons. Is it a D sugar? No, it's not. I'm going to look at my highest numbered chiral carbon. That's the way that I like to approach this, because I like to give myself a reminder of, think about which carbons are chiral carbons. Every time that I go back and say, how many chiral carbons are there? Because I guarantee you, I will have questions about chirality and chiral centers on these molecules. So I'm going to think, okay, I need my highest numbered chiral carbon. Boom, it's that one. Even if I've forgotten pieces of information, but I remember, oh, well, that is the one that I look at, that one right there, that's my highest numbered chiral carbon. Whenever I'm taking my exam, I might look back and be like, well, if that's chiral, Then the carbon above that also is chiral, of that is chiral, but that one right there is not chiral. Does everyone follow that? So my highest numbered chiral carbon, which is overall carbon number 5 on a hexose. I've got a hydroxide group on my left-hand side. L for left, it's not L for left, it's actually L for levo rotary, because this goes back to how it rotates light. You know, dextro rotary, levo rotary. So this is an L sugar because I have a hydroxide group on my left-hand side of this molecule. Does everyone follow that? Okay. My other molecule. Okay, well, that's a D sugar. Great. Now, what I need to remember about the differences between L-glucose and D-glucose is that they are mirror images of one another. So what that means is, if I gave you a structure and I said, hey, convert this D-glucose to L-glucose, that does not mean that you just go to that highest numbered chiral carbon and flip that. Well, if we look at this, translating D-glucose to L-glucose, carbon number 5, we're moving the hydroxide group to the other side. Carbon number 4, we're moving that to the left-hand side. Carbon number 3, we're moving the hydroxide group to the right-hand side. Carbon number 2, we're moving the hydroxide group from the right-hand side to the left-hand side for this L-glucose. So when you make that L to D conversion, don't just switch one carbon, or don't just switch that highest number chiral carbon. You're instead coming up with a mirror image of that other molecule. And that's the thing that people have a tendency to make a big mistake on. Does that all make sense? Okay. Now, I always like to bring this up. These are enantiomers. They are mirror images of one another. Your body and enzymes within basically every single organism that has been identified is sensitive enough to detect the difference between D-glucose and L-glucose. But one thing that I've always heard is that D-glucose, if you put that on your tongue, it tastes sweet. L-glucose, if you put that on your tongue, that also tastes sweet. The difference between these is that 1 gram of L-glucose is like $35.
What?
Okay, so then if you think 1 gram of sugar, man, if you wanted to get a Coca-Cola that was sweetened by L-glucose, that would be like a $35 and it's like 60 grams of sugar on there.
Well, 0 sugar.
Zero, okay.
It's so 0.
So let's say that if it's $30, then we're talking about, you know, that might be like just for simplicity's sake, that's like a $2,000 soda almost. Here's the thing. Your taste buds will like be stimulated by that sweetness. But all of the enzymes in your body in glycolysis won't do anything with that L-glucose. So it will pass through your body like an artificial sweetener. So ultimately, if you could cook up a way to make L-glucose and L-glucose in bulk, you're just going to be printing money. Because it's a sweetener and it's not going to be tasting weird, but there's not going to be any caloric value. I always just think that's kind of interesting because when most, if not all of your sugars, it's very rare for an L sugar to be employed in a biological setting. It's very rare for L sugars to be found. D sugars are the way to be.
Do you know if food that's made with L-glucose?
No, it's I did a PubMed search not too long ago, like last year or 2 years ago, whenever I was teaching this class. And I was like, surely there's got to be some like microorganism that's found like in a thermal vent or something like that, that just makes L-glucose as an intermediate. And it's like nothing. And, you know, that's just, I'm guessing that there's probably some enzyme out there that does it, but I think that, you know, this is stereochemistry that has to do with the enzymes that are involved in making it, and all of the enzymes are made up of amino acids that have a particular stereochemistry. So how would you invert those? Well, you'd have to make different, anyway, I just,
That's weird.
it's elusive. It's weird, but it's an opportunity is what it is.
Make money out of it.
There you go. Okay, so enantiomers are molecules that are mirror images of one another. Diastereomers are molecules that are the same chemical type. So two aldoses that are the same number of carbons can be diastereomers, provided that they are non-mirror images. Now, if you were to compare an aldose and a ketose, could they be diastereomers of one? No, they could not, because they are not the same chemical type. A 5-carbon and a 4-carbon aldose, could they be diastereomers of one another? No, they could not, because they're not the same size. And then if we go back here, these enantiomers, they are your mirror images of one another. Are they diastereomers? No, they are not, because they are mirror images as opposed to not mirror images. So D-glucose and D-gulose are examples of mirror images. Notice we continue to come back to D-glucose as our reference point. There's a handful of sugars that I do expect you to know the structures of. Glucose is one of them. It's the most biologically relevant sugar. So I think that it's a good one to know both in its linear form and its cyclic form, which we'll get to after a little while. And I'll show you the other examples that I want you to know. Okay, so there's our blunt as could be, our difference between these two sugars. Now, another class, another term that you need to be familiar with is sugars that vary because of only one carbon. These are epimers of one another. D-glucose and D-galactose are epimers of one another. The only difference between glucose and galactose is this carbon right here. In glucose, we've got the hydroxide group on the right-hand side, and galactose, we've got the hydroxide group on the left-hand side. These two sugars are referred to, or these are an example of a pair of sugars that would be referred to as C4 epimers of one another. So C1, 2, 3, 4. C1, 2, 3, 4. C4 epimers, the only difference between them is that hydroxide group on carbon number 4. Does that make sense? Okay, grand. So big terms, enantiomers are mirror images. Diastereomers, they got to be the same type, size, and non-mirror images. And then epimers are an example of a diastereomer. However, the only difference is at one carbon. Cool? Okay, so we've looked at sugars in their linear form, and now what we're going to do is look at their cyclic form. So if we look at this, one of the things that we started with when we were talking about carbon number 1 and aldose, carbon number 1 has a partial positive charge. If you look at all these hydroxyl groups, specifically, if we look at this hydroxide group right, oh, you know what? I need to just use the highlighter function. There we go. That hydroxide group, that hydroxide, that hydroxide, that hydroxide, that hydroxide. All of those hydroxide groups, if you were to say partial charges on them, do you think that a hydroxide group has a partial charge? Yeah, it's fair to say that. Partial, negative, or positive? Negative, because it's got those lone pairs of electrons, two on top, 2 on bottom. So if we've got a partial positive charge coming from that carbon right there, conceivably that partial positive charge could react with the partial negative charge on the hydroxide on carbon number 2. Would everyone agree with that? And we would make a ring. And how large would that ring be? It would be 1 carbon, 2 carbons, and 1 oxygen. So 3 members. What do we know about 3-membered rings from organic? Oh, super, super uncommon. They super don't like each other, or they don't like existing. And aren't epoxides, aren't those 3-membered rings? Those like to pop open. That's what I remember. So 3-membered rings, unlikely. So what I'm going to do is I'm going to erase my highlight on carbon number, or hydroxide number 2. What about the hydroxide on carbon number 3? Then we're talking about, that'll be a 4-membered ring. Even closer, but we're getting something that looks like a square. So that's not particularly favorable. It could happen, but it's not super likely. Carbon number 4, the hydroxide group, oh, lo and behold, that would give us a 5-member ring. That's a little bit better. The hydroxide group on carbon number 5, that would give us a 6-member. That's even more favorable. Then the hydroxide group on carbon number 6, that would give us a 7-member ring. So these 3 hydroxide groups are all potentials for this carbon to react with, but I've highlighted these 4, or the hydroxide group on carbon number 4 and carbon number 5, because those are the closest proximity to our carbon in 3D space of this linear molecule. Because this linear molecule, it's not just, I'm standing up straight, I do not move. Instead, it's like there's motion to it. So I'm going to go ahead and erase that last one right there. So we have this cyclization that takes place due to partial positive and partial negative charges. And I'm going to go ahead and just take one moment to announce this. I'm recording. We are at about 56 minutes. Should anyone need to step out and go to the restroom, you do not need to ask for anything of that nature. I know that there's always someone who's like, oh, I was waiting to ask to go to the bathroom. Similarly, like yesterday, I don't plan on pausing and saying, all right, well, here's our break, other than this announcement right here. So if you need to step out, I'm recording it. I'm going to post it on our Canvas page so you can get that. All right, there we go. So here's what that cyclization is going to look like. So we have carbon number 1, this oxygen right here. Where is that oxygen coming from? This is a place where lots of people get mixed up. On 5? Is that what you said? Okay, sorry. Yes. Should have just. Yeah. I'm happy that you said the hydroxide group on carbon number 5, because that oxygen becomes one of the members of our ring, and that oxygen comes from this hydroxide on carbon number 5. Now that's always confusing, especially when we look at a figure like this. I'm going to highlight a couple of other atoms here. So highlighter, this oxygen right here is that. This hydrogen is that. And it's kind of tough to see, but these are intended to be in like the same plane. So this is carbon number 1. Does everyone see that a little bit? Okay. So when we cyclize, this double bonded oxygen becomes a hydroxide group. This hydroxide group right here becomes a carbon oxygen carbon bonded molecule atom. Now with that in mind, let's look back at carbon number 1. On the left-hand side, we have carbon number 1 with how many different things bound to it? 3. Okay. Now let's jump over to the molecule on the right-hand side. Let's look in at carbon number 1. How many different things does carbon number 1 have bound to? 4. And they're different, right?
Yeah.
Yes. Okay. So carbon number 1, when we're talking about an aldose, is that a chiral center? Yeah. But when we cyclize it, carbon number 1, is that a chiral center? It is. So we've gone from a linear molecule with 4 chiral centers to a cyclic molecule with 5 chiral centers. That's an important distinction, because when we cyclize these sugars, we gain a new chiral center. This new asymmetric center, or this new chiral center, is also known as a anomeric carbon, or an anomeric center. Is everyone good with that? Okay. Now, we're going to come back to cyclization in just a minute, but I want to introduce you to all of the aldoses, and I want you to know the 5 aldoses that are the most important aldoses. D-glyceraldehyde, D-ribose, D-glucose, D-mannose, D-galactose. Those 5 sugars are your most important sugars. Now I bring up glyceraldehyde, and now I'm going to jump over to our ketoses. So when we have our 3 carbon glyceraldehyde molecule, 1, 2, 3. Does everyone agree that that's 3 carbons? Okay. Then we've got dihydroxyacetone, 1, 2, 3 carbons, right? Okay. Now, if we were to travel back in time for a moment. To right here. When we had our 6 carbon doubly phosphorylated fructose molecule, we split it in 2. We got 1 molecule of glyceraldehyde phosphate. 3 carbon sugar with what functional group? Aldehyde or a ketone? An aldehyde. It's right there in the name, glyceraldehyde. Then we also got dihydroxyacetone phosphate, a 3 carbon molecule that is a ketose. I like to bring this up because when you take 4375, it's very easy to just be like, okay, cool, there's a 3 carbon molecule, there's a 3 carbon molecule. Those are different because they have different functional groups. Neat. And then you go on and take metabolism and you see this and you're like, okay, GAP, DHAP, it doesn't matter. There's no rhyme or reason for any of this. So the way that I think is helpful to think about this is when you go from fructose 1,6-bisphosphate to glyceraldehyde 3-phosphate and dihydroxyacetone phosphate, you're going to take fructose, which happens to be a ketose. You're going to cut that ketose in 2, and you're going to get an aldose and a ketose. You're going to get a phosphorylated aldose and a phosphorylated ketose. I think that's helpful just because there's a tendency for people whenever they're trying to learn glycolysis to just be like, okay, I gotta know the names. And then I gotta know the names of the enzymes. And then, oh man. And I full disclosure, the way that I triaged this information when I was learning it was, what's the simplest information that I need to know to get some points? Well, the simplest information was like the names of the molecules. Okay, well, the names of the molecules, that's intimidating. Could I do something like acronyms or like initials? Okay, cool. GAP or G6P, F6P, FBP. Okay, cool, got that. And then I'd be like, okay, well, now that I feel good about that, I'm gonna dig a little bit deeper. I'm gonna learn what G6P stands for. And then I would dig a little bit deeper and I'd be like, okay, I feel good about this. And then this particular step, I would know, oh, it's glyceraldehyde 3-phosphate and dihydroxyacetone phosphate. And I could come up with those 2 names very easily. But if you gave me either one of those structures, any information I had ever learned about what the hell an acetone or a ketone or a aldehyde was, does not exist anymore. I would look at those 2 structures and I'd be like, well, each one of them is phosphorylated 1 time. Maybe I can write both of the names so unclearly that it kind of looks right. And then what I'd also do, and this is what I like, I see many students do the same thing to me, where I give the molecule and then they write glyceraldehyde 3-phosphate above both of them, and then dihydroxyacetone phosphate below both of them. So then if I was to say like, hey, which did you mean? They'd be like, oh, well, you know, which one was right? And I'm like, I know exactly what you're doing because I did that. So my point is, when bringing this back up is, you know what an aldehyde is. I'm sorry for swearing. You know what an aldehyde is. You know what a ketone is. We know what these 2 basic molecules look like. Glyceraldehyde, aldehyde is in that phrase. Well, we've got carbon number 1, that is our aldehyde functional group. Carbon number 2, carbon number 3. If I gave you this molecule and said phosphorylate it, you'd be like, well, where do I phosphorylate it? Glyceraldehyde 3-phosphate. would that give you a little bit more information to where it's going to be phosphorylated? The hydroxide group right there is going to be replaced by a phosphate. Does that make sense? Then over here, dihydroxyacetone phosphate. Well, this is what dihydroxyacetone looks like. Dihydroxyacetone phosphate. Do you think that is different than a molecule like dihydroxyacetone bisphosphate? Dihydroxyacetone phosphate suggests that there's one phosphate group there. Well, if you were to draw it on this lower hydroxide group, would you be wrong? As opposed to the one that's higher? No, you wouldn't. Because that immediately would become priority number one, wherever you drew that phosphate. Does that make sense? Okay, so now let's go back. Glyceraldehyde 3-phosphate. The way that this figure is set up is there's no biological relevance to the synthesis of these hexoses. So some people like to look at this and then be like, oh, well, or the way that I personally like to look at this is I like to say, okay, what's more complex than a 3-carbon sugar? A 4-carbon sugar. What's more complex than a 4-carbon sugar? A 5-carbon sugar. What's more than 5? 6-carbon sugars. This does not show that glyceraldehyde is used to synthesize erythrose. Erythrose is not used to synthesize ribose. This is instead just showing a comparison. D-glyceraldehyde. There's no other way that you can rearrange the atoms on that molecule to make another D sugar that is different from D-glyceraldehyde. Does that make sense? D-erythrose. Okay, well, now let's think about that D terminology, D versus L. These are both aldoses. So carbon number 1, which I'm going to highlight. Carbon number 1, that's fixed. That has to be your aldehyde. Carbon number 4, those are also fixed. Those have to be CH2OH. Does that make sense? These are both D sugars. What does that mean for carbon number 3? Those both have a hydroxide group on the right-hand side. Does that make sense? So the only thing that could give us different 4-carbon sugars or aldotetroses is if we had a OH on the right-hand side versus an OH on the left-hand side. Do I expect you to know the names erythrose and threose? I don't. The ones that have boxes around them are the molecules that I expect you to know. If we were to look at D-erythrose and D-threose, could we describe them? Absolutely. The best term to describe those two molecules is to say that they are C2 epimers of one another. Because they are basically the same. They are not mirror images. The only difference between them is the hydroxide group on carbon number 2. Now, if we were to look at D-ribose, well, when we talk about D-ribose, about to try to draw, highlight in red on the canvas up there. D-ribose and D-arabinose. For those, carbon number 1 and 5 are fixed. 4 is fixed because we're talking about a D sugar. 3 for these two is going to be identical. And then carbon number 2 is where we have variation between these two. This is why it's kind of like, oh, well, it's almost like a progenitor of, or it's almost like these are arabinose and ribose are built off of erythrose. But it's not a synthetic, instead it's just like modeling building. Does that make sense? So that's what we've got with those sugars, arabinose, ribose. If we were to compare arabinose and xylose, let's go ahead and let's look at just arabinose and xylose. Okay, so carbon number 2 for arabinose and xylose those are different from one another. Carbon number 3, those are also different from one another. So are these epimers of one another? No, they're not. They're diastereomers, but they're not epimers. Does that make sense? Okay. Now, can we say anything about D-xylose and, or if we look at, if we look at D-xylose, we can say that D-xylose and D-lysose, they are C2 epimers of one another. Would everyone agree with that? Okay. Now, if we look at D-xylose, does it have any other epimers other than D-lysose? You're absolutely right. D-ribose. It's not a C2 epimer, it's the C3 epimer of xylose. Because the difference between, if we compare, and it is helpful to just go carbon by a carbon. D-xylose and D-ribose. 1 identical. 5 identical. 4, 4. Then 2, 2. But 3, 3, that's where we have our variation. Does that make sense? Okay, grand. Then glucose, mannose, galactose, it's going to save you a lot of time just to be able to recognize, okay, glucose and mannose, what's the difference between those? Well, C2 epimers, okay? Glucose and galactose. Galactose is a C4 epimer of glucose. So if you can remember that, that's going to save you a bit of time. Okay, cool. So these are your important aldoses.
Are D-ribose
will-
and it's so sorry. I was gonna ask, are D-ribose and D-xylose, are those diastereomers?
They would be, because anything that's an epimer is also diastereomer. So if you think about diastereomer as like the big umbrella, a subsection of the diastereomers is the epimers.
Okay, thank you.
Sure thing. That was ominous. I did not expect that, but anyone who's on Zoom, feel free to talk. It will just strike me, and so you will see me and my horrible poker face. So, okay. Yes. C3 epimer, because the variation is carbon. C3 epimers. Cool. Great. Okay, ketoses. Dihydroxyacetone. That's your 3-carbon ketose. Ribulose, fructose. Fructose is sometimes referred to, well, I would venture to say commonly referred to as the ketose version of glucose. And for that, let's bounce back and forth between fructose and glucose. First and foremost, I think that it's beneficial to you to, if there's like a structure, okay, which is the first structure that I want to know? It's glucose. That's the first structure that I want to know. And let me tell you just a little bit of a suggestion. Whenever I think about glucose, what always comes to my mind is right, left, right. That's the first thing that comes to my mind, because like I said previously, we're focused primarily on D sugars. So we don't really care about L sugars quite so much. Now, with that in mind, if I know that I'm dealing with a D aldose, what does that tell me? It tells me carbon number 1 has my aldehyde functional group. Okay, so do I need to concern myself with the configuration of carbon number 1? I don't. Okay, then this is an aldohexose. Well, that means I don't need to worry about carbon number 6 because that's not a chiral carbon. Then as a D sugar, I also don't need to worry about the hydroxide positioning for carbon number 5, because by virtue of it being a D sugar, that hydroxide group is on the right-hand side. Does that make sense? So whenever I hear glucose, I think right, left, right, because what I see is my hydroxide group on carbon number 2 is on the right-hand side. My hydroxide group on carbon number 3 is on the left-hand side. My hydroxide group on carbon number 4 is on the right-hand side. So when it comes to looking at my hexoses, you know, when I was an undergrad or grad, there was some time where my professor expected us to memorize all the hexoses. And, you know, there's lots of mnemonics, and some of them are clever. The more crass they are, the easier they are to remember. But I remember one of my classmates was like, you really don't need to remember 6 carbons. You really need to know 3 carbons, 2, 3, and 4. The positioning of the hydroxide groups on 2, 3, and 4, how those vary. Because 1, 5, and 6 are going to be identical for all of your D sugars. Does that make sense? Okay, so now if we go with glucose as right, left, right, carbon number 2 has the hydroxide group on the right-hand side. Yeah. Okay. If fructose is the ketose version of glucose, well then this carbon right here can't really have that hydroxide group. Instead, it's got my ketone, my double bonded oxygen. So that means that carbon right there is effectively that one right there. This carbon right here and this hydroxide group is that one right there. Which also means that carbons 5 and 6, and actually when it comes to knowing ketone structures, you even have less to remember. Because these top 2, you don't need to worry about those. CH2OH and C double bonded O. Then these bottom 2 right here are that COH and CH2OH. So effectively, when it comes to knowing the structures of your ketoses, there's really only 2 carbons that you need to know when it comes to your ketohexoses. But fructose is commonly referred to as the ketose version of glucose for that reason right there. It's structurally very similar to it. Okay, now for the cyclization of sugars. We've already kind of identified the atoms that were in play, but here's some of the important terminology. We have an aldehyde that reacts with an alcohol to form a hemiacetal. A hemiacetal can react with an alcohol to form an acetal. A ketone reacts with an alcohol to form a hemiketal. Hemiketal reacts with an alcohol to form a ketal. Your basic ring structures, you have either a 5-membered ring or a 6-membered. The terminology for your 5-membered rings and 6-membered rings is based on a pyrran ring and a furan ring. When we have a sugar that forms a 6-membered ring, does anyone want to guess how we integrate this as to that terminology? I've got a head shaking of no, I don't want to guess. You're absolutely right. A pyranose, a 5-membered ring sugar. What do you want to guess now? A furanose. So we can implement that or integrate that as a part of our terminology. Now, with that in mind, we have alpha D glucopyranose. There's also alpha D beta D glucopyranose. Okay. Now there's a bit to dissect there. Carbon number 1. I think that it's helpful to highlight that carbon. And remember, that is our carbon number 1. This hydroxide group right here, that is that oxygen. That carbon number 1 is our new chiral center. So that carbon right there no longer that carbon right there is now a chiral center, so it has 4 unique things bound to it. Those 4 unique things are the ring going in the direction of the oxygen, the ring going in the direction of the carbon, the hydrogen, and the hydroxide group. Now, the positioning of these hydroxide groups is significant. This carbon number 1 is referred to as an anomeric carbon. That anomeric carbon is going to designate whether we're talking about an alpha or a beta sugar. An alpha sugar is one in which our hydroxide group here is pointing downward. Our beta is where our hydroxide group is pointing upward. Now, there's a little bit more to that definition than that, but I would say 98% of the time, if you are asked a question about alpha versus beta designation, you're going to get it right. Should you follow hydroxide down, hydroxide up, down is alpha, up is beta. Now that last 2%, where we can kind of get the nuance to that definition. We want to put this hydroxide group on carbon number 1 and compare it to carbon number 6 with respect to our ring. These two things, this hydroxide group for carbon number 1 and carbon number 6, are pointed in opposite directions from our ring. So this one is pointing down from our ring, and this hydroxide, or this carbon number 6 is pointed up compared to our ring. And if you think about, or the way that that's kind of expected is you think about this as like, that's your axis right there. That's your central axis. So is it pointing below the axis or is it going above the axis? Does everyone follow that right there? Okay. Now, that is an alpha designation where those two groups are pointed in the opposite directions. When those two groups are pointed in the same direction, then you have a beta designation. Does that make sense? So this hydroxide group and this carbon are both pointed up compared to the central axis of our ring. So alpha and beta, these two sugars right here would be referred to as an anomeric pair. Now, like I said previously, whenever I look at glucose, I think right, left, right. The other thing that I think is down, up, down. So I translate right, left, right to down, up, down. Because in what is known as a Hayworth projection, which is the way that I want you to draw sugars, and I think is the convention, I know is the convention to draw sugars, is we're going to draw our 6-membered or our rings where these two bonds are parallel to one another. So basically, if you're drawing a sugar, it should be 2 parallel lines, a portion of a triangle, another portion of a triangle. You can do that with ASCII art in your computer. Alligator mouth and equal sign. There we go. Perfect. But carbon number 2, my hydroxide group is pointing down. Carbon number 3, my hydroxide group is pointing up. Carbon number 4, my hydroxide group is pointing down. So right, left, right is down, up, down. Now, many people are always curious, oh, well, is that always going to work? Is that going to work every single time? And my answer to that is, as long as you are drawing a D sugar, yes. Now, we're not drawing an L sugar. Why not? Well, one thing is, we started very broadly. We talked about linear sugars, and now we've narrowed it down from all these possible sugars to now we're cyclizing sugars, and we're focusing in on a cyclic sugar of glucose, D-glucose, a very, very common sugar. Can an L sugar be drawn in or represented in a ring form? Absolutely. Is that of high importance, or is that high value information? Not particularly, because that molecule is not a high value molecule. Now, with that in mind, how would you draw that? Well, basically, you'd be inverting every single group and you'd be drawing a mirror image of this molecule. So what that would look like is something a little bit more like this. Oh. Sorry about that. Oh, and then this is going down. Didn't get much better. But you can absolutely draw a L sugar in the linear form. But again, it's not biologically relevant. You're not going to see it very often, but it is something that can exist. So in that case, right, left, right, down, up, down, does it really track? Yeah, it does. But if you are given like an L sugar or L glucose and asked to draw the cyclic form of D glucose, which I'm not going to do that, because I'm going to stay in the realm of like what's relevant, then you'd have to account for that change there as well. All right. So I just bring this up, drawing sugars, in this form that I just erased, because what tends to happen is people draw sugars, and I know that we're not going to be drawing things very often, except largely in practice, but they have a tendency to draw a sugar like this. Now, is that fundamentally wrong for drawing a 6-membered ring with an oxygen as one of those members? No, it's not. But what happens is when someone takes this molecule from their memory, and then they start out with a structure like this, what they end up doing is they end up drawing this right here. And they say, there you go, there's my carbon number 6. Now, is that carbon number 6? It's not. If they wanted that to be carbon 6, it would be drawn right here. So my recommendation is to model all of the sugars that you draw and study off of molecules like this and this. Do they exist like that in living systems? No, they exist in a chair and boat conformation, but this Hayworth projection isn't a otherwise fairly accurate way of looking at sugars, and it's appropriate and relevant. So monosaccharides exist almost entirely as 5- and 6-membered rings. Anomeric carbon is that new stereocenter, that new chiral center. Anomers are carbohydrates that differ in configuration only at the anomeric carbons. The two anomers can interconvert in solution in a process known as mutarotation. So this alpha D-glucose can be converted to beta D-glucose. Now it's nice to think that it's just like, oh, it's like a pinwheel that hydroxide group spins up or something like that. It's really not that simple. Instead, this ring has to open up, then a rotation takes place, and then the ring closes back up again. So there is I believe it's the beta configuration. The beta configuration is the more relevant and more abundant form of those two sugars. Okay, so here's another rendering of that cyclization. And boom, there we go. Fantastic. If you're looking at the PDF, are you going to get that? No, you're not. You're not going to get that animation. Other ways that sugars can be converted, cyclized, is if we take something like fructose. Fructose can form a 5-membered ring, as we see with alpha D fructopyranose, but it can also form a 6-membered ring, as we see down here with alpha D fructopyranose. Now, ways that I keep straight the terminology of furanose for a 5-membered ring starts with F. Furan 5. Pyran does not start with an F, so it's not 5. I don't really have anything beyond that. It's just, letters. I remember the difference. Hayworth structures, beta and our alpha, right, left, right, down, up, down. One thing that's always important is to always remember, whenever you're looking at a sugar, it's to identify your anomeric carbon as quickly as possible. Not quickly, but that should be your first objective. Identify my anomeric carbon. So if I'm talking about glucose, my anomeric carbon is carbon number 1. So is this hydroxide group really a part of my down, up, down? No, it's not. My down, up, down starts with carbons 2, 3, and 4. And that's how I come up with this being glucose. Good? Okay, cool. Common furanoses, fructose and ribose, fructofuranose and ribofuranose. Conformational isomers, sugars can exist as chair and boat formations, or here's your chair and boat formation of beta D glucose. I'm going to stick with the Hayworth structures. And that's just because that's pretty much the biochemist convention. I will show some chair configurations, however, when we talk about polysaccharides, because cellulose, for example, is going to exist as the chair conformation, and cellulose is something that we can't digest, in part because of the linkages between the different monomers, but also because they have this very dense network of hydrogen bonding. So that's why you can't go outside and start eating bark off the tree and get any nutrients from it. So there's your chair, there's your boat. Okay, cyclic structures. Yeah. There we go. I feel like that's a good spectrum right there. Okay, functional groups on sugars can be reduced. So when you see these functional groups of a cyclic sugar, we have a couple of them. For starters, we've got the hydroxide groups. We've got a bunch of them here, here. We've also got Joe Dirt's favorite functional group, a hemiacetal. We also could have a hemiketal. So when you think about those functional groups, I would most be focusing on my hydroxide groups as places where we can have a modification. Now, when we talk about hexokinase, did we talk about any sort of modification of one of those hydroxide groups? Hexokinase took ATP and transferred a phosphate group onto carbon number 6. And what we got was, rather than hydroxide here, we had CH2OPO3. As evidenced by this right here. So the second molecule, glucose 6-phosphate, carbon number 6 has that OPO3 minus. That's where that phosphate group is added. So then we rearrange that molecule and we phosphorylate fructose 6-phosphate to put another phosphate group on to make fructose 1,6 bisphosphate. So that's what we got going on. Yes, I want to keep them, but I'm also not done. How many slides? Okay, there we go. 32. Ooh, 51. This is gonna be a quick 8 minutes. Share. Okay, so functional groups on sugars can be reduced. One form in which they can be reduced is the sugar glucose can be reduced, and rather than an aldehyde, we're going to have an alcohol up there. That reduction is going to give us sorbitol. Sorbitol is produced naturally from glucose. It can be used as a sugar substitute because it is metabolized very slowly. However, natural production due to elevated level of glucose in the case of diabetes contributes to cataract formation and nerve damage. So that's something that is always kind of a health-related indicator. Ribose. Deoxyribose is a product of the reduction of ribose, where the hydroxide group is removed, and instead we have a hydrogen giving up D2 deoxyribose, which is a building block for DNA. Deoxyribose versus ribose. Ribose for RNA, deoxyribose for DNA. Reduction of ribose component of nucleotides is a critical step in the synthesis of deoxynucleotides needed for DNA synthesis. Sorbitol, as I looked at just a moment ago, also is commonly known as well as glucatol. Sucralose is a artificial sweetener that is a modified form of a disaccharide, which when you see this, there we go, that chlorine there. Now, other ways that monosaccharides can be modified is to form disaccharides. There's 3 common disaccharides that I want you to know: sucrose, lactose, maltose. Sucrose is a disaccharide between glucose and fructose. Lactose is a disaccharide between glucose and galactose. Maltose is a disaccharide between glucose and glucose. Now, here what we have is one of these disaccharides. We've got a 6-membered ring. Now we've got a 5-membered ring right here, but a 6-carbon molecule. So this is sucrose. Now, what I want you to notice about sucrose here is a couple of things. First of all, we've got glucose and fructose. We've got our numbering of our carbons. Carbon number 1 has a hemiacetal, where there was a hydroxide group on carbon number 1 from glucose. We see that hooking up with a hydroxide from fructose. So we have a hydroxide, or what was a hydroxide group there. So when you think about the synthesis of something like sucrose from glucose and fructose, it is a hemiacetal reacting with an alcohol. So hemiacetal reacting with an alcohol is an example of a acetal form or acetal form. Now, this is what is known as a 1,2 glycosidic linkage. So sugars that have, yeah, an alpha 1 beta 2 glycosidic linkage. Here's another depiction of sucrose, where we have that beta configuration there. Glucose, fructose. Now, these other sugars, lactose and maltose. If we think back to what lactose is a disaccharide between glucose and, I'm not going to tell you what it is. If you remember it, fantastic. But let's look at these two sugars. When you think glucose, I want you to think down, up, down on carbons 2, 3, and 4. Okay, so this where I'm putting my highlight is glucose. So that means that this other sugar, well, is it glucose? Let's find out. Carbon number 2, I have a hydroxide group going down, 3 is going up, 4 is going up. So it's not glucose. But it is, however, the C4 epimer of glucose. What is the C4 epimer of glucose? Galactose. So that's why this bulk of material is like, yeah, you're learning foundations, but then you got to kind of dig back into them in order to bring up some of this other information. So this is what is known as a 1,4 glycosidic linkage. Maltose, well, we've got on the left-hand side, 4, or well, down, up, down, and then down, up, down. So that would be, that's also, it's glucose and glucose. A beta 1,4 glycosidic linkage connects this lactose molecule, and an alpha 1,4 glycosidic linkage connects the maltose molecule. Now, I bring this up because what some people have a tendency to do is when they look at a disaccharide and when they look at a disaccharide, they'll say, oh, okay, well, the hydroxide group going up or going down, it doesn't really matter. That doesn't influence my name or anything like that. It absolutely does. It is absolutely still relevant to the nomenclature of that specific sugar. So I like to look at this model of lactose because then you can say, okay, well, I'm going to look at this disaccharide and figure out, is it glucose? Yes, it is. Is this other one glucose? I know what glucose is. It's down, up, down. If it's not down, up, down, is it glucose? No, it's not. So when we looked at maltose, we said down, up, down, that's glucose. Down, up, down, that's glucose. Okay, so this is disaccharide between 2 glucose molecules. When we looked at lactose, well, it's glucose and something that's not glucose. What is that something that's not glucose? Well, that happens to be lactose. Does that make sense?
Yes.
Okay, great. That was a desperate yes. Yes, if you'll stop talking, please. It's been enough. This is the last thing that I want to talk about. And this is just whenever you look at a sugar, you can designate, and this is particularly important when we talk about disaccharides, polysaccharides. You can identify a free anomeric carbon versus one that's bound to something. If we look at ribose, our anomeric carbon is highlighted here, and that anomeric carbon gives us our ketone, or our hemiketal. Okay. Then if we look at lactose, we've got what should be a hemiacetal. Oh, but lo and behold, it's bound to where there was an oxygen. So that would be an acetal. Then we've got another anomeric carbon where we have a hemiacetal. If you see in a molecule where there is at least one free anomeric carbon, that sugar is considered a reducing sugar and has, where that hemiacetal or hemiketal is, has a reducing end. What that also means is that the opposite end of this sugar, if we look at specifically, if we look at this lactose right here, this is referred to as the non-reducing end of the sugar. So we've got a reducing end where there is a free anomeric carbon, and then we have a non-reducing end where there is not a, well, there's an alcohol, but there's not a ketal or hemiketal. So sugars are classified as either reducing or non-reducing sugars based on whether or not they have at least one free anomeric carbon. If a sugar does not have any free anomeric carbons, that is considered, much like sucrose, a non-reducing sugar. When you see a non-reducing sugar, more than likely you're going to see a linkage that is between, or sorry, you're going to see a glycosidic linkage between two anomeric carbons. Does that make sense?
And you said they were based on if they have a what?
If they have a free anomeric carbon. Okay, cool. Well, I'm going to go ahead and stop right here. And this is where I'm going to pick up on tomorrow's day. I guess